Hello and welcome back to the lab. In today's video, we're going to finish work on the HP Model 400H Vacuum Tube Voltmeter. When we left off, I had disassembled the meter movement itself and cleaned up the problem we were having with the sticking needle on the voltmeter. I reassembled everything and found that the instrument was basically working, although it was reading about 10% high, way out of spec, but it was reading about 10% high, but the instrument was basically working. Um, I had mentioned that I had ordered a operating and service manual for this instrument, and I was waiting for it to arrive. And in fact, it has arrived, and so now we will finish working on the instrument. Okay, let's turn it on its side here. We were looking at and considering whether to replace some of the components in this instrument, specifically these Black Beauty style paper capacitors, which have a propensity to fail, to develop leakage over the years. The paper insulation tends to absorb moisture and create a leakage path, which can be uh, actually very bad for your instrument. These capacitors are, in the most part, coupling capacitors interstage between the various stages of the tube to couple the AC signal from the plate of one tube into the grid of the following stage. Um, so you don't want any leakage in those capacitors because the B plus that's on the plate of the one stage will end up on the grid of the following stage, or at least a small segment of it, which will cause excessive plate current in that stage and burn out that tube and perhaps the power transformer and all kinds of other things. So you don't want any leakage in these capacitors. They do have a propensity to develop leakage throughout the years. So I wanted to take a look on the schematic to see where these particular ones are in the circuit to see if they may be a problem. Also, I wanted to look at replacing the selenium rectifier with 4 silicon diodes and modernize that circuit. So let's take a look at the schematic and see where these components are located in the circuit and whether or not we can consider replacing them. Okay, so here's the schematic of the 400 well, it's actually the schematic for all of the 400 series voltmeters. The 400D, the 400H, and the 400L all use the same circuit. The only thing different within the 3 different variations is the meter movement itself over here. So this is the schematic for all 3 of those versions. Over here, CR3, we see the selenium rectifier. As it turns out, that's not in the high voltage part of the circuit as I suspected, actually. Um, it's actually in the heater, the filament circuit, it to provide 12.6 volts DC to the filaments of some of the tubes, specifically the earliest stages of amplification. As it turns out, even a small amount of AC that is present on the filaments of this high gain amplifier section of the instrument will cause issues further down the road as that ripple is amplified. So instead of using AC to drive the filaments, they use DC for these earlier stages. Now, some of the later stages do use AC in their filaments. So there are two tubes connected in parallel, and then 2 more tubes connected in series in parallel also. But those 2 sets of 2 are connected in series. So each of these is a 6.3 volt filament. DC, these are driven with DC voltage, which that DC is produced by the selenium rectifier. There's an adjustment using this little pot right here, this trimmer pot, um, to set that filament voltage to plus 12.6 volts DC. And I have measured that voltage and made that adjustment, and we do have exactly 12.6 volts DC at this point. Um, In fact, when I measured it originally, it was about a volt low. It was measuring about 11.6 volts, but I dialed it to exactly 12.6 with the pot and measured it carefully and waited for everything to stabilize and settle down. So there is 12.6 volts DC exactly. That means the selenium rectifiers are working. There's really no need for me to change them, and I don't suspect they will ever fail because it's only a 12.6 volt DC circuit. There's no high voltage or high current really in that part of the circuit. So I'm just going to leave the selenium rectifier in the circuit because it's currently working just fine. Now those interstage coupling capacitors that I was concerned with, here is one here. The C19.1 microfarad goes from the plate of V2 into the grid of V3. There's another one over here, C24, that goes from the plate of V3 into the grid of V4. And there's another one at a different, in parallel with the first one, C23, a 0.1 microfarad that goes from V3 to V4 as well. There's a coupling capacitor over here between V4 and V5. That's this C28. Now, this one is not one of those paper capacitors. It is, in fact, one of those mylar capacitors that were in the circuit. Those do not typically fail, so I'm not concerned about that capacitor. But these two and this one here, I am concerned about. There is a fourth one of those Black Beauty style paper capacitors. It turns out that it is over here in the power supply regulator circuit. Um, this is not so critical. If it develops a small amount of leakage, it's not going to cause a catastrophic failure of the instrument. So I'm not too worried about replacing that one over here. It's just used in the startup of the regulator circuit of the high voltage supply. um, Once this capacitor charges to its voltage, full voltage, it effectively is disconnected from the circuit and no longer has any function in the circuit. It's only used at power up. Okay, so what we want to do is see if there are any leakage in these three capacitors. This one over here, this one over here, and this one here. These are all those three Black Beauty capacitors. Um, Easiest way for me to check for leakage is to simply measure the voltages differential between the plate of that stage and the grid of the following stage. You want the grid to be more negative than the cathode, of course. That will prevent the tube from running away and drawing too much plate current and frying not only the tube, but also perhaps your power transformer and other components in the network. So when I measure the voltages on the grids of these tubes, they are in fact more negative than the cathode. In fact, the voltages that are required to be on those grids are written right here on the schematic. And if you measure them, they're very close to what it actually says. That tells me that none of these capacitors are actually have any leakage whatsoever, or at least not enough to impact the function of the circuit, which I probably suspected already because the instrument is working. So I'm not going to replace these capacitors either at this time. However, I am going to place an order with one of those part suppliers to buy replacement capacitors for these so that I will easily and readily be able to replace them in the future should a problem develop with this instrument. And I'll keep those capacitors on hand to do that. So the bottom line is I'm not going to change any components in the circuit. Now, also, I was concerned about the carbon composition resistors, which all have a propensity to drift out of tolerance over time. And in fact, when I took a random sampling of many of those carbon comp resistors. It turns out that almost all of them are reading about 10% higher than they should be. Almost all of them. And in fact, for the most part, they are 10% tolerance components. So they are right at the very limit of their specifications right now. but the instrument is working. It would be pointless for me to replace all of these carbon composition resistors to bring them back into tolerance if the instrument is working. Um, if it wasn't working, that would be a different story. The instrument is currently functional. I'm going to leave all of those resistors exactly as they are, and just go through the calibration procedure and see if I can bring all of the measurements of this voltmeter into its original factory specs. All right, so I have completed the realignment calibration procedure for this unit off camera because it's long and boring and kind of tedious, but I wanted to show you the process and show you where the adjustment points are inside the instrument so that you can see what the process was that I went through. Basically, we start by calibrating it on the 1 millivolt range. So we dial this all the way down. It's turned off now and unplugged, but I just want to show you how it works, how we do it. So it's set to the 1 millivolt range. We apply 1 millivolt at 400 hertz and adjust this pot right here for the basic to make it read 1 millivolt at 400 hertz. We change the frequency to 4 megahertz and adjust the capacitor to compensate for the 4 megahertz to make the instrument read at 4 megahertz. We also come down here and adjust this pot on this side, the low frequency response, for the correct response at 10 or 20 hertz on the 1 millivolt range. So we have an input of 10 or 20 hertz, and we adjust the low frequency response with that pot. Then we switch to the 1 volt range, and there is a pot down here, R101. You can't see this one over here, R101, that will adjust the 400 hertz response at 1 volt. It'll adjust the input attenuator of this instrument. And there's a compensation capacitor C4 over here that we adjust that at 20 kilohertz. This cap adjusted at 20 kilohertz. And then we also check the frequency response at 4 megahertz to make sure that this capacitor hasn't thrown the 4 megahertz response out of tolerance as well. Oh, the very first one I forgot to mention is this pot right here. This is the 12.6 volt DC adjustment for the selenium rectifier that controls the filament voltages of those first stages of tubes. This is the 12.6 volt pot that you use to adjust that. So once we've adjusted the 1 volt range on the input attenuator over here, we come back around over here, and we have two more compensation capacitor trimmers over here. This one is for the 3 millivolt range at 4 megahertz. I'm sorry, 3 millivolts at 4 megahertz. And this one down here is for the 10 millivolts at 4 megahertz. We adjust those until we have the correct readings on the instrument for all of those. I have gone through all of those adjustments, and each of them reads perfectly. I wanted to show you the equipment that I use as a calibration standard, what the source of the voltage that I'm using. So let me turn the camera over to those instruments now. Okay, so here are the two instruments I use to calibrate AC voltmeters. And these are, in fact, the same two instruments that I used when I worked at Hewlett-Packard back in the 1980s to calibrate AC voltmeters. I'm using the exact same equipment, the same model numbers. These aren't the exact uh, same ones, but they're the same model numbers I used 45 years ago to do the same job. On the bottom, we have the 740 HP 745A AC calibrator. It goes from 1 millivolt up to 100 volts with an external 1000 volt amplifier. There's a times 10 amplifier that you can add to it to calibrate above 100 volts up to 1000. I have the amplifier It's behind it over here. You can't see it, but it's back over there, and but it's not working currently. I have to do a repair on that amplifier. I have completed the repair on the 745A. Before I started making YouTube videos, I completed the repair on the 745A. So I will, in fact, do a video or two on the work that I did on the 745A to get it in its functioning condition. There was considerable work, actually, but I wasn't making videos at that time. So I did that work about 2 years ago. And so that's the 745A. Now the 745 goes from 10 hertz up to 110 kilohertz, um, but it won't go higher in frequency than that. And so for the higher frequencies, we need an oscillator like this one. This is a 652A test oscillator. It goes from 10 hertz to 10 megahertz. So it can be used to test high frequency response of AC voltmeters. And that's what we used back in the 1980s to test these voltmeters like the one I'm working on today. Um, this one goes from 1/10 of a millivolt full scale all the way up to 3 volts full scale. I can't test higher than 3 volts above 110 kilohertz with using these two instruments. So I can test every range and every frequency on this instrument except for the 300 volt range. I don't have uh, a calibration standard that can output 300 volts AC at this time. Once I get my amplifier fixed, I will solve that issue, and then we'll be able to test everything, including the 300 volt range. Now, so what we do is we set up the 1 millivolt at 400 hertz. We dial up the frequency to 400 with this knob, and we set it at 1 millivolt. Apply that voltage to the input of the meter through this banana cable, right, that I have connected to my output over here. That goes to the input of the 400H under test, and I make the adjustment to make 1 millivolt full scale reading on the 400H instrument. Then I take this 652 test oscillator output, which is a BNC cable. I'm going to set it to 1 millivolt also. The BNC cable goes through a 50 ohm termination into a BNC to banana adapter into the input of the 400H voltmeter under test. I set this instrument also to 400 hertz, which it is right now, and I adjust it for the same reading that I had with the 745A, so that the 400 hertz reading from this instrument matches the 400 hertz reading from that instrument. Then I can adjust the frequency up to as high as 10 megahertz, readjust the amplitude so that it matches, and test the frequency response of my 400H under test. I can continue that with each range, each amplitude range in this instrument. So I've tested all of the ranges and all the frequencies, and tested the entire instrument. I can also use the 745A to test the linearity and tracking of the meter movement of the 400H itself by dialing down this output. So I can go 1 millivolt, 900 microvolts, 800, 700, 600, etc. So this has 1, 2, 3, 4, 5, 6 decades of adjustment. It's an AC voltage standard, and I can use that to test the linearity of my unit under test. So that's what I used to calibrate my 400H, and it turns out that it comes into complete, perfect calibration with 0% error on every single range. It's really quite remarkable how accurate this old vacuum tube voltmeter really is. And in case you think I'm making it up, I wanted to demonstrate that to you. Here we have 1 volt at 400 hertz, 0.9 volts, 0.8 volts, 0.7 volts, 0.6 volts, 0.5 volts, 0.4 volts, 0.3 volts, 0.2 volts, 0.1 volts. In every single case, it is absolutely spot on. Let's do something with higher resolution. Let's try halfway. 5. We'll do 0.56789. 0.56789 volts. Looks to me like about 0.568. It is absolutely spot on. No deviation from the actual input voltage whatsoever. This instrument has a 1% tolerance, and it's far, far better than that, even though it is, 55 years old. Quite remarkable, I think. I don't know about anybody else, but I'm really excited about this. I really am. All right, let's take a quick look at the frequency response of this instrument as well. Let's hook it up to the 652A test oscillator and see how it does frequency-wise. Okay, so now we're looking at 20 hertz at 0.9 volts. It reads 0.914, a little tiny bit high at 20 hertz. Let's do 200 hertz. It is spot on at 200 hertz. 2 kilohertz. It is spot on at 2 kilohertz. At 20 kilohertz. It is spot on at 20 kilohertz. At 200 kilohertz. It is spot on at 200 kilohertz. And finally, at 2 megahertz, it's reading a tiny bit high there as well. 0.90, I don't know, 907, something like that. And let's go all the way to 4 megahertz that this instrument is supposed to go to. Right there, it's reading quite high there, 0.914, something like that. It's reading about 1.4% high at 4 megahertz. All in all, very, very good frequency response on this old meter. I'm very pleased with this, very pleased indeed. One thing I forgot to mention on the HP 400H, and in fact all of Hewlett-Packard's analog AC voltmeters, is that the low terminal on the input is actually connected to earth ground. It's connected to chassis ground, which is connected to earth ground when the line cord is plugged in through the third wire of the line cord. So you cannot make floating measurements with this instrument. It's grounded at the low terminal. If you try to make floating measurements with this input, you will blow something up. So please don't do that. Always make sure your low terminal is at 0 volts potential with respect to earth ground. Otherwise, you will have some serious repair work to do. All right, so there you have it. I'm very proud to add this beautiful piece of vintage test equipment to my collection, and I look forward to putting it to practical use in my lab. The HP Model 400H Vacuum Tube Voltmeter. Thank you very much for watching. Please like and subscribe, And stay tuned for more fun videos with vintage test equipment. Thanks again.